Good morning. Today we continue the review of probability theory and its connection to machine learning. And as we mentioned last week, that machine learning, one major target of the machine learning is to resolve the uncertainties in data. And when we mention about uncertainty, then there is the main tool to deal with uncertainty is probability theory. And most algorithms in machine learning can be derived based on probability theory, or at least it can be explained and to see the limitation of the algorithms based on the probability theory. Because of that, probability is very important to study in order to understand the many algorithms in machine learning. Last week we talked about this important relation about the conditional probability, and we explained it in details, and we said that this means that the probability of event B, given that event A has occurred, that is equals probability of A and B divided by probability of A, and from this also we derived the primitive form of Bayesian theorem. Okay. So this is also, we have discussed it. We discussed it last week, where we can, if we know that the probability of A if B has occurred, then we can also derive the probability of B if A has occurred. And also we gave simple example on the whiteboard when we talk about how to use it, or to use this concept in building some machine learning basic application. Okay. This actually conditional probability is very important, and many times it explains things in different way that how we think about. For example, if you know that one guy, he has 2 children, and it is equally likely to be boys or girls, so they are equally likely. So the probability that to be boy or girl is 0.5, 50%. And if they have, if he has 2 children, then we have all possibilities that we might have boy and boy girl, or girl boy and girl girl. So this is all possibilities that we have. Now, if we want to know what is the probability that if he told you that one of my children is boy, then what is the probability that the second one will be always boy? Because the second one can be boy or girl. So intuitively, if you think in this way, so it is 50-50, so it is still 50%. But now if we look to this sample space, because he told you that one of them is boy, then this possibility will be like will be taken out from the space that we think about. Then here, if the first, or if one of them is boy, what is the probability that the second one will be also boy? This will be boy, and we have those 3 conditions, or 3 possibilities. Then the least probability is only 1/3. So it is half. It is not half anymore. So when we start think about the conditional probability, it might many times give like results that it is not like intuitively that we think that the result should be. Okay. And of course, the probability that the second will be girl is 2/3. Okay. And I'm not going to explain this mathematically because we have many things to give today, but I give you just another example. There is one famous game that if you have 3 doors, and behind one door there is a car, for example, one of them, so you don't know them. So if you assume that there's a car here, and the other 2 doors, there's nothing. So they are empty, nothing here. Okay, and this is a game. So in the game, they asked you to select one of those doors. So in the beginning, for you, because it is unknown, so the uncertainty is maximum. So your uncertainty about where is the car is, for this door is 1 over 3, 1 over 3, and 1 over 3, because you don't know anything about the condition. So you can select any one randomly. For example, you selected door number 3, for example. You said that I selected number 3. So the opponent, what he will do, he will open door number 2. And you see there's nothing behind it. Okay? And then he asked you, do you want to keep 3 or you want to switch? Do you want to keep 3 or you want to switch? Intuitively also, there should be 50-50%. But the probability theory they say no. If you switch, you will increase your chance to win. It will be 2 over 3. So in probability theory, there are many things like this that they are very interesting to apply and very interesting also to understand how it works. Also, in probability theory, if we have 3 events like A, B, and C, okay, if probability of A is greater than probability of B, and probability of B is greater than probability of C, it is not necessary that probability of A is greater than probability of C. So they are different applications in probability that we can if we have time, we can also explain some of those interesting behaviors in probability. Okay, now here we have the probability of different events like BI1, BI2 until BIK. So in order to say that those events are like independent, then the probability of any set of them should be the multiplication of probabilities. So probability of BI1 and BI2 is the same as probability of BI1 times probability of BI2, and so on. So any, for example, if let's say A, B, and C are independent to each other, then probability of A, B, C equal to probability of A times probability of B times probability of C. But not this only. Also, B, probability of A, B is equal to probability of A times probability of B. And also probability of A, C is equal to probability of A times probability of C, and so on. So you should have all conditions that they will be this is the condition that all of them, they are independent to each other. The law of total probability, if we have some space like this S, which can be partitioned by like events like B1, B2 until B6, and there's certain event A here, but all those events, like from B1 until B6, they are disjoint events. So there is no intersection between them. And the probability of A, in this case, probability of A equal to what? Equal to probability of A and B1, the intersection between them. So probability of A will be like probability of A and B1 plus probability of A and B2 until probability of A and B6. And in that case, we know from conditional probability that probability of A given B equal to what? Equal to probability of A and B, okay, divided by probability of P. Then, by multiplication, we got probability of A and B, B1 or whatever, equal to probability of A given B times probability of B. So we can substitute for each one of those. Then probability of A equal to probability of A given B1 times probability of B1 plus probability of A given B2 times probability of B2 until the sixth one. So this is called the law of total probabilities. Total probabilities. This will be used later, as we will see in at least in one example. Okay. Because probability of BI given A equal to probability of A given Bi times probability of Bi divided by probability of A. But we know that probability of A can be represented by this summation. Then we can use it in this way. Okay. Marginal probability that if we have any space, sample space, which can be partitioned by two disjoint events like A's and B's, then we can represent any one of them by if we know the others. Okay. Okay. This example here, we will take this quite simple example to see how to use the conditional probability to solve some problems. Understanding those concepts will be beneficial in order to understand also several game theory applications for this. So here they said that a quality control test is 95% effective in detecting damaged mobile phones. So we have like a quality control in mobile phone factory. So every mobile comes to the quality control in order for fast testing. If for example, if there is external damage of the mobile or there is software bug in the mobile. So they test the mobile, and this quality control effectiveness is 95%. What it means? It means that if the mobile has any damage, there is a chance that 95% will be detected. Okay? Because of course you cannot spend very long time for testing every mobile. So the quality control should be fast. So in that sense, it is 95% effective in detecting damaged mobiles. However, the test also yields a false positive result for 1% of the good mobile phones. What it means? Sometimes the mobile is good, but still it says that it has some defect. In that sense, this mobile will be like thrown or taken out from the serial mobiles. In that sense, the probability of error in that case is 1%. So only 1% of the mobiles, if they are good, they will be like decided that they have some certain kind of damages. It is also known that 0.5% of the total mobile phones have some kind of damages. So from where this number? From database. So because for some certain company, they sell a lot of mobiles every year. Some mobiles come back to the company, return it back to the company with some damages. So the company knows that 0.5% of their mobiles, they have some kind of damage, either physical or software. Okay. For a test of a certain mobile phone, the quality control test was positive. So we have now certain mobile, the quality control test positive. It means that this mobile should have some damage. Okay. What is the probability that the mobile is really damaged? So now we like, based on this information, to find what is the probability that it has damage. You can see that this example, little bit like, it can be confused for some people, but with the rule of conditional probability, it becomes very easy to understand and also to see what will be the result. So now let us define some event. So we define K as the event that the tested mobile is damaged. So K, that means that the mobile is damaged, really. The mobile is damaged. Okay? And we define C that we have positive test. So C, there is positive test. Positive test. Because as we know that when it is positive test, it is not necessary that the mobile is damaged. As we say before, that it is only 1% if the mobile is good to be like decided that it has some damage. Okay. Now, what we are looking for, we got positive test. So for example, the red alarm is on. So the mobile has some damage. They told us that the mobile has some damage. Now we like to see what is the probability that the mobile is damaged really. So now we compute the probability that, what is the probability that the mobile is damaged really given that we received a positive call or a positive test. In that case, we use the conditional probability or the Bayesian probability or the Bayesian rule that it is probability that you receive a positive test given that the mobile is really damaged times the mobile is really damaged divided by the probability that you receive a positive test. Okay. Now let us see what is the probability that you will receive a positive test if it is really damaged. It is given. It is 95% because we said that it is 95% effective to capture the damaged mobile. So this one is 0.95. We know it. Okay. What is the probability that the mobile is really damaged? We know from data that it is 0.5%. We know that from data, like historical data, that we have 0.5% the mobile have some kind of damage, so it is 0.005. Okay? And then, what is the probability that we receive a positive test? The probability that we receive a positive test, it has two options. It has two cases in this example. First, that we receive a positive test given that the mobile is damaged, times the mobile is damaged. Or we have another possibility that we receive a positive test given the mobile is good. So it is K bar, it is the complement of being damaged times probability that K bar. So we have only two cases here. This is the rule of total probability as we explained now. So it is the probability that you receive a positive like test given the mobile is really damaged, time probability the mobile is really damaged. This is the same as the above term, plus the second one, that the probability that you receive a positive test allow that the mobile is good. This probability is given also because it is 1%. We said it is 1%, so this one is 0.01. Times what is the probability that the mobiles are not damaged? It is 1 because the probability that the mobile is damaged is 0.005. Then the probability that the mobile is not damaged is 1 minus 0.005, which means that is 0.995. Okay? So we substitute these values in the equation. Then we got 0.323. So we got about only 0.3 probability that the mobile is really damaged. So this result actually indicates that this quality control is not good. Because now the probability that the mobile is really damaged is only 30%. Okay? The mobile is really damaged is only 30% or 32%, which indicates that this quality control is not effective. Okay. Now let us see why it works in this way. Why it works in this way? Why we got this number? Because in the beginning, if you know that it is 95% effective, and the false positive is only 1%, you will think in the beginning that this quality control is very good. But now it indicates that when you got a good, positive alarm for the mobile, that it is only 30% that the mobile is really damaged. And if we want to understand why we got this result, let us see that if we assume that the company produced 100 mobile, okay? So we have 100 mobile produced by the company. Okay. Now, on average, there is 5.5% of the mobiles to have some kind of damage. So out of 100, okay, let us say 1,000. So to have some number. So the company produced 1,000 mobiles. Okay. And out of this 1,000, there will be 5 mobiles. On average, they have damage, some kind of damage. Okay, there will be 5 mobiles because these 5 0.5% means 5 per 1,000. Okay. Now, our quality control effectiveness is 0.95. So out of those 5, there is most likely that our quality control is very good to capture those damaged mobile with probability 0.95. So let's say that they will capture all of them. So all of them, those 5, will be captured as they have some kind of damage. But this test control, it has 1% of error. Okay, what is the meaning of 1%? If out of 1,000, there is 1% error, it means that for those who, which are good mobile, it will produce about, because of course we have to subtract this from this, but about 10 mobiles, good mobiles, they will be detected as damaged mobile. Because it is 1%, 1% of 1,000 will be 10. Okay. Then in this case, the total is 15. The total that they will detect that as damaged mobile, 5 which are really damaged, and 10 which are good. 5 plus 10 is 15 mobile. So the probability that it is really damaged will be 5 divided by 15, which will be about 0.33, which is very close to the number that we got. So this is the explanation why we got this number. But actually, the conditional probability give it in more straightforward way. So actually, with this conditional probability and Bayesian theorem, we can resolve and analyze much more complicated problems. Okay. Is this the Bayesian classifier? I explained it already last week, but we will go through it fast. So the probability, if we have certain classes, from class 1 until class n, and we have some attributes from x1 until xm, then we are interested to find what is the probability that those attributes belongs to certain class. So that is what is the probability that we are in class I given those attributes. Using like Bayesian theorem, we can solve this in this way, or expand this probability in this way. So it is probability that the attributes given the class, the probability of the class divided by the probability of the attributes, regardless of the classes. Okay, and this one is called posterior probability. This part. This part is called the likelihood. Okay, and this probability of Ci is called a priori probability or class priori probability, and this one is called the evidence, the probability of x1 and x2 until xm. Here we assume that all x and the classes are discrete, and also the likelihood or the attributes are discrete numbers. If they are continuous, we should use the probability density function, as we will see later. Not now, but when we talk about the continuous random variables, we will talk about these cases. Okay, so using this form, we can compute, because as I explained last lecture, this likelihood could be computed or estimated actually from the data that we have. And also this number could be explained from the data. We have only problem here about the evidence. The probability of x1 and x2 until xm, many times those attributes are correlated, or they are dependent to each other. Okay, and of course we can also look for them in data, but sometimes the data are not large enough in order to find the correlated results or the real probability in this case. And we can solve it by using naive Bayesian classifier. In the naive Bayesian classifier, we have some assumption that all attributes are independent. All attributes are independent. In that case, this probability of x1 and x2 until xm simply equal to the multiplication of them. So this simplifies the probability computation. Okay. However, this may reduce sometimes the accuracy, but it works in many applications. Okay, so we have one example. it is very similar to the example that I explained last week. So now we have two attributes like x1 and x2, and we have classes. So we have two classes, either A and B, or B. So we have, for example, if it is 0, 1, then we have class A. If it is 1, 1, we have class B. So we assumed here that the attribute x1 belongs to 0 or 1, and x2 belongs to 1 and 2. So we have discrete numbers. And based on this data that you have, like historical data that you have, and now you have new data like 1 and 2, x1 equal to 1 and x2 equal to 2, and you would like to see in which class that you should project this input. Is it class A or class B, based on the Bayesian classifier. Okay, now we have the probability of Ci given, because now it is given that x1 equal to 1 and x2 equal to 2, it is given, and this equal to the probability of x1 equal to 1 and x2 equal to 2, given Ci, probability of Ci. So we need to compute it, because here we have two classes, A and B. So I will compute first for class A, and I compute for class B, then I selected the larger one. Okay, so with class A, assuming that we are class A, what is the probability of A? What is the probability that you are in class A? In this data, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12, the total number of data. How many that we have class A? So it is 1, 2, 3, 4, 5, 6, 7, 8. So 8 of them are in class A. So the probability of being in A is 8 divided by 12 as an estimation. So it is 2 over 3. And this is the probability of B. Of course, it will be 1 minus this number, which will be 1 over 3. Okay. What is the probability that x1 equal to 1 and x2 equal to 2 given class A? So what we do here, we check A, and we check 1 and 2. So this one is not counted. This one is not counted. We count this one because x1 equal to 1, x2 equal to 2, and it belongs to class A. So we have one here, one case. Here we have another case, two cases, okay, and only two cases. How many we are in class A? 8 times. So the probability will be 2 divided by 8. It will be 1 over 4. And the probability of x1 equal to 1 and x2 equal to 2 given B, we do it again. So we check with B, 1, 2, and B. So this is 1, 2, 1, 2, no. This one is B. This is the only one that we have. How many B's we have? We have 3. We have 4. 1, 2, 3, 4. Then this probability is 1 over 4. Now we can substitute here. Of course, we can also calculate probability of x1 equal to 1 and x2 equal to 2, or we can assume the naive Bayesian as requested here. So it will be the probability of x1 equal to 1 times the probability of x2 equal to 2. And then we got this probability of A given x1 and x2 is equal to 0.8, and the probability of B given x1 and x2 is equal to 0.4. In that case, of course, we will select the class A. We will select class A. So this naive Bayesian classifier is one very fast machine learning that you can use for your data. So, for example, if you have very large database, you can easily read this data and classify your new input. One simple way, if you have like numerical number, not classes like or not discrete like this one, that you can use like intervals. You can divide them into intervals, and then you divide them again. This is one simplification into discrete. For example, if one of the inputs is the age, for example. So age can be from 1 year or from 0, newborn, until let's say 100 years, that you have all numbers. Then you can divide them into intervals, like from 0, let's say, to 3, you give them like 1, and greater than 3, and up until, for example, 10, you give them 2, and so on. Then you have discrete. So you can divide it into discrete. If you have voltage, for example, if you are working with some machine that generates some voltage, and voltage is between, let's say, minus 5 volt until 5 volt, which is like continuous. So also you can divide them into intervals, like intervals. Every interval, for example, is 0.5 volt. Then you have 10 intervals. This is one simplification for the continuous case. But the more general that we should use the probability density function, as we will explain it later. Okay. Random variable. What is random variable? So far we were talking about events. So we said that K is the mobile is damaged. C, positive test. If you like to draw some for example figure about the mobile is damaged with the positive test, it is difficult because they are not numeric. They are events. We talk about events. And head and tail, for example, it is events. So they are symbolic. Okay, we need, and it is very important in probability theory that we need to deal with numbers. So random variable is the mapping process between event space to real numbers. So actually we have here events, for example, events, and then we convert from events to real numbers, from -infinity to infinity, to the real numbers. This mapping is called random variable. It becomes much easier to deal with the probability theory space in the probability theory. Okay, and it is very important in the measure theory also to deal with numbers. Okay. For example, in the case of throwing, let's say, 2 or 3 coins, okay, tossing 3 coins, then and we call the random variable y is equal to the number of heads that we receive, number of heads. Now we start to talk about numbers. In the beginning we say head, tail, head, and so on. But it is difficult to deal with these symbols. Now we have numbers. So here y is the number of heads. Okay. So if you throw 3 coins, then you might have 0, means that all of them are tails. Then we have 1 or 2 or 3. Now we talk about numbers. Okay. In that case, if we have like head, tail, and head, tail, then we have tail, head, tail, head, and we have, of course, 8 outcomes. Then what is the probability that you have probability that y equal to 0? Is equal to what? It means that all of them are tails, which means if they are equally likely, this will be 1/8. Okay. What is the probability that y equal to 1? Simply we count how many events that we had only one head. So for example, we have this one, it is 1 here, and 2. So we have 2, and we have, for example, here 3. Okay. Then we have 3 cases where we have only 1 head. And probability that y equal to 2 means that how many events that we have 2 heads. So in that case we have 1, 2, 3. Okay. So we have 3 also. Okay. So we have 3, for example, over 8, and 3 over 8, and then probability that y equal to 3 means that all of them they are heads. Then it is 1/8. The summation must be what? 1. The summation must be 1. If the summation is not 1, it means that there is 1 missing. There is something wrong, because this is the summation of all possibilities of the random variable. So here we call y as a random variable. Okay. We might need sometimes, for example, if I asked you what is the probability that y is greater than, or what is the probability that, let's say, y squared is greater than 3. Okay, y squared greater than 3 means that the probability that y greater than plus or minus square root of 3. Or because it is always positive, so we can say greater than square root of 3. In that case, we are interested to compute y greater than, for example, 1.7 something. Okay, probability that y greater than 1.7. Okay, this is it means that not this one. This is one. Yeah. So it means that this one and this one. So this is the same as probability of y equal to 2 plus probability of y equal to 3, and in that case it is equal to 4 over 8 equal to half. Now, when we convert from even space to real numbers, it becomes easy to say y square root of y, tan y, cosine y, because we start talking about what? Numbers. But how could you do this one if you are talking about head and head tail or tail head? You will not be able to do that. So the main target or the main objective of using random variable, that it simplifies the analysis, because we start talking about numbers instead of symbols. Even actually in the die case, that we have dot or 2 dots or 3 dots and so on. So actually, previously, when we talk about 1 dot, we deal with it as a symbol, not a number. So it is what is the probability that you receive 1 dot? Now 1 dot is even. Okay, but now we can say that y, random variable, is equal to number of dots. For example, a pair. In that case, now it becomes numbers. Why? It can be 1 or 2 or 3 or 4 or 5 or 6 as a number, not as event, not as an event. Okay? So it is very important to deal with random variables. One example, for example, if you toss a coin with the probability B to get head, how many numbers you will throw this coin until you receive the first head? So you might, when you throw the coin, so our random variable now is n, the number of tossing the coin. So n is the number that you toss this coin, because we stop until we continue until you get the first head. The probability of getting head is b. It means that the probability that you get tail is 1 minus b, because we have only 2 outcomes from this experiment. So you throw the first one. What is the probability that n equal to 1? It means that the first tossing of the coin, you get head. So this probability equal to b. Probability that n equal to 1. What is the probability that n equal to 2? What it means that the first one was was tail, and then the second one was head. So the probability of getting tail is 1 minus b. This is the first outcome. Then the second one was b. What is the probability that n equal to 3 is equal to, it means that the first one you get tail, the second you get tail, the third you get head. So it becomes 1 minus b times 1 minus b times b. So it means 1 minus b squared times b. And we continue this way. So the probability that n equal to, for example, n small is equal to 1 minus b times n minus 1 times b. And of course, it can be until infinity. We go in this way. Okay. So now we have our random variable is n. Our random variable is n. And in that case, we can also draw it. So we have n random variable. It can be 1. For example, this is 1. It can be 2. It can be 3. It can be 4, and so on. So this is the probability of getting 1. This is 2, 3, and 4. And of course, it goes to 0, because every time b and 1 minus b, the maximum is 1. So it means that if it is 1, then you will have only 1, because 1 minus 1 equals to 0, and the others will be 0. If it is point, like 0.5, 0.7, whatever, so every time you multiply by a fraction of 1, then you go in this way until you reach to 0. So the probability becomes very, very small at the end. Okay. Now it becomes easy to draw the results, because now we deal with random variables. A random variable can be also continuous, like in this case. So for example, what about the temperature? If we draw how the temperature changes in Vasa, of course, I added this. So this is all the slide, because now this year it seems that very strange. But previous, that in February, for example, the temperature can be something like that. from minus 30, and it is very low probability to be in positive, but always the highest probability will be in the negative side of the temperature. So this is based on the history. So we built some uncertainty figure which reflects our uncertainty about the changes of the temperature. Okay, but the temperature can be anything. It is not discrete, like this one. This one discrete that we have first toss, second toss, and so on. But this one is continuous. The temperature can be anything between, for example, minus 10 to minus 20. For example, it can be anything. So we have infinite number of possibilities between in those intervals. In that case, we have continuous distribution. We call this one as a probability density function. We call it as a probability density function. And the probability density function is given by this equation that we can calculate the probability of any interval in that random variable x by integrating over that set. So if we are interested to know the probability of certain set B, then the probability that x, random variable x, belongs to B is equal to the integration of f of x dx. Okay, and some of the properties of the probability density function, that the probability density function is always positive, greater than or equal to 0 for all values of x, and also the integration from minus infinity to infinity. If you integrate over all possible random variable values, so the result will be 1. In other words, the area under the probability density function equals 1. Also, we can compute the commutative distribution function. So the commutative distribution function is the probability that random variable x less than or equal to certain number a. So in that case, based on this relation, so we can also calculate the integration from minus infinity until a, because x less than or equal to a, so integration from minus infinity until a of the distribution f of x dx. This gives us the commutative distribution function of any random variable x if you know the probability density function of that x. And from if you know the distribution function and you want to know the probability density function, because the relation is integration, as we can see, then fx of x is the differentiation actually of the CDF at a equal to x. We are going to see those several times, so we will explain it during the course when needed. In the discrete case, we call it a probability mass function. So in continuous, we call probability density function. In the discrete case, we call it probability mass function, where the summation of probability of discrete random variables is equal to 1. And also, we can compute the commutative density function of x in that case. Like in this example, we show that the CDF is always increasing function. Okay, let us stop here for the break, and then we start after the break to see several like random distributions, discrete and continuous. We have 15 minutes break. Hello again. So we continue. The distribution functions, either discrete or continuous. Discrete, like we call probability mass function as this one, or the continuous case, like probability density function. They are like models to describe the behavior of the uncertainty. Models to describe the behavior of the uncertainty. The simplest description of uncertainty is the case where we have only two outcomes from the event, like the head and tail, for example, success or fail, a winner or loser. So we have only two outcomes from this event. In that case, we can describe them like two events, P and 1 minus P. P and 1 minus P. So the probability of 1, it means that the probability that x equal to 1 and this equal to P, and then x equal to 0 is 1 minus P. In that case, we describe the success with a random variable 1 and the fail with random variable 0, for example, or head with random variable 1 and 0. Not necessarily, of course, to be 1 and 0. You can put any numbers, but 1 and 0, or 1 and minus 1, for example. So you can describe what kind of number that you give for your problem. So if it is 0 and 1, then we will have probability of 1 is p, and then probability of 0 is 1 minus p, because we have only two outcomes. The second more general case, that if we repeat this Bernoulli random variable, this one is called Bernoulli random variable, if we repeat it in times, so in that case, we have another random variable y, and y equal to summation of those xk. Xk can be 0 or 1. It can be 0 or 1. So in that case, y, it can be 0 if all x's are 0, or it can be 1, it can be 2, 3, until n. So the maximum that you will have is n. For example, if you repeat this example, if we throw this coin 3 times, not 1 time, 3 times, and then we count the number, that y equal to like x1 plus x2 plus x3. Okay. If we call the head like 1 and tail is 0, okay. So in that case, y, it can be, if all coins were tail, that will be 0 plus 0 plus 0, and this equal to 0. So y starts from 0, and the maximum of y, it can be of course 1, 2, and the maximum is 1 plus 1 plus 1, and this equal to 3. In this case, we call this case that like binomial random variable. Binomial random variable. So y can be 0 or 1 or 2 or 3 in this experiment. So if we repeat a Bernoulli random variable in times, then we got that the binomial random variable. Okay. So what is the probability that you will get 0? What is the probability that y equal to 0? It means that all experiments gave tail. If the probability of getting tail is 1 minus p, and the probability of getting head is p, so this will be 1 minus p cubed. Why? Because the first is tail, the second is tail, the third is tail. What is the probability that y equal to 3? It means that the first is head, the second is head, the third is head, so it becomes also p cubed. P times p times p. Okay. Now, what is the probability that y equal to 1? It means that what is the probability that you will get 1 head and 2 tails? In that case, it will be b times 1 minus p squared. Is it enough? No. Why? Because now this is the first tossing, for example, the first time, the second time, and the third time. Okay. Now we like to compute the probability that we get only 1 head out of this experiment. So in that case, it can be like head, tail, tail. It can be also tail, head, tail. It can be tail, tail, head. In these 3 cases, we have only 1 head. So every one, the probability is p times 1 minus p squared. 1, 2, 3. So it can be this one or this one or this one. They are mutually exclusive. If one of them happen, the others cannot happen. In that case, we multiply this by number 3. Multiply this by number 3, because it can be this one or this one or this one. Okay. Also, if we like to compute the probability that y equal to 2, means that we got 2 heads in this case. So it can be b squared times 1 minus p, okay, because 2 heads and 1 tail. And what is the number here? Let us see. So we might have like head, head, tail, or we can get also head, tail, head, or we can get head, head, tail. We don't have other possibility. And that yes, so tail, head, head, yes. So now we have how many situations? We have 4 cases. So it can be this one or this one or this one or this one. Huh?
Third one
The
is
first one
is repeated.
This is head, head, tail, and head, tail, head, 2, and yes, this one is repeated. Yes, you are right. Yes. So it is tail, head, yes. So we have 3. So now we have this one first, or this one, or this one. So again, we will have 3. Okay, and so on. In that case, if you have like 4 or 5 or 6 events, it can be very complicated to count it in this way. So, but we have general formula that we can use for computing the binomial. This is the binomial element. It is given by, for example, if you want to compute it, so it is given that probability. What is the probability that you get y equal to, as we said, 0 or 1 or 2, so it is equal to, let's say, k out of n. So if we have n cases, for example, if we repeat n times, what is the probability that you get k? This is given by n, k, this is the binomial element, okay, times probability that b, because the probability of getting 1 is b, so b of the power k, 1 minus b times n of the power n minus k. So this n out, or k out of n, is given by n factorial divided by k factorial times n minus k factorial. So in that case, you can compute, for example, we said here we repeat 3 times, so it means that n equal to 3. If you like to see what is the probability that you get y equal to 1, what is 1 out of 3? This would be 3 factorial divided by 1 factorial times 3 minus 1 factorial. So this will be 3 times 2 times 1 divided by 1 factorial is 1, and 3 minus 1 is 2 factorial is 2. So 2 cancels 2. This will be a 3 as we obtained before. So you can calculate it for any situation. For example, if in football match, we know that certain player that, based on the history, that he scores the number of goals that he scored, let's say 100 goals that he himself scored, we then, let's say, 500 or out of 500 goals done by the same match. So we know that this guy can match 0.2, like probability 0.2, that he scored that goal himself. Okay. Now you heard about a match in this football game, and you know that team scored 5 goals. Okay. What is the probability that that player, let's say, score 2 out of them? Okay, 2 out of them. So in that case, we call that if he scored, then the random variable equal to 1. If he doesn't score, then this random variable equal to 0. So in that case, we are looking for, out of 5 goals, what is the probability that he scored 2 of them? So it is 2 out of 5. The probability is 0.2 out power 2, and 0.8, 1 minus 0.2 is 0.8, of the power 5 minus 2 is 3. So in that case, it becomes 5 factorial divided by 2 factorial. 5 minus 2 is 3 factorial times 0.2 square 0.8 to the power 3. In this way, you can compute the probability that 2 out of 5 had been scored by that specific player. Okay. So how to compute this one? You can do it in different ways. For example, you can say that this is 5 times 4 times 3 factorial, divided 3 factorial, and 2 factorial is equal to 2. So 3 factorial cancels 3 factorial, and 2, 1, and this will be 2. So 2 times 5 equal to 10. So it will be 10 times 0.2 of the power 2 times 0.8 of the power 3. So this is the probability. So if I asked you, what is the probability that at least he scored 1 goal? Okay. So in that case, the probability that at least, what is the meaning at least he scored 1 goal? It means that he scored 1 or 2 or 3 or 4 or 5. So it becomes like probability that, what is the probability that y greater than or equal to 1 is equal to probability that he scored 1 plus probability that he scored 2 plus probability that he scored 3 plus 4 plus 5. But instead of computing all of them, those many times, so we know that the total probability, if you add probability that y equal to 0 equal to 1, the total probability equal to 1. So this is the same as probability as 1 minus probability that y equal to 0. To be the same. So you don't need to compute every one. So it is the same as 1 minus probability that y equal to 0, which means that 1 minus probability that y equal to 0, that 0.2 of the power 0 is 1, and then we will have 0.8 of the power of what? 5. Of the power of 5. So this gives the probability that at least he scored at least one out of 5. Okay. So this is the binomial random variables. It can be also in if you have data. If you made some survey, and in that survey, for example, you have you ask the question about this machine learning course. Is it good or bad? Okay. So then you make the survey, because this is the third time given, about maybe about 200 students total. So you ask it all of them out of those 200, and let's say that 50 said the course is good and 150 said the course is bad. Okay. So the probability that the course is good based on the survey, good, that equal to 50 divided by 200. Okay. And the probability that the course is bad, so it is 1 minus this number, or it is 150 divided by 200. Okay? And then if I take randomly 6 students or 7 students, we take randomly 7 students. What is the probability that 2 of them will say that the course is good? It is another form of binomial distribution. So in that case, it will be 2 out of 7 times the probability that to say it is good is 50 divided by 20. So it is, let's say, about 4 of the power 2, and then 3 over 4 of the power 5. Then you can compute the probability in this way. So the binomial distribution, or the binomial random variable, it can describe a lot of different kind of problems if they can be classified into 2 cases: success and fail. Success and fail, head and tail. So in that case, we can apply this binomial random variable. However, remember that here we assume that all trials are independent. All trials are independent. So this is a strong assumption that it is given here. Okay. This is the survey example. Here it is one code for those who like to work with R, than to emulate this example. Okay, so hypergeometric distribution, we can skip this one. Multinomial distribution is important as well in case that you have more than two outcomes, because as we said, we have success and fail. But if we have multinomial, it means that we make this survey of the course, but we don't give only 2 options, bad or good course, but we put like excellent course, and very good, and good, and so-so, and bad. So we give 1, 2, 3, 4, 5 options. In that case, we cannot model this problem with using binomial, because binomial you have to have only success or fail. You have 2 options, but here we have 5 options. In that case, we use what is known as multinomial distribution. Multinomial distribution is very similar to the binomial, but it is given in this way. So the probability that you have, for example, based on this survey, we found that 0.1 probability, 0.1%, or 0.1 probability that say it is excellent, or 10%, and 0.1 say they very good, like 0.5 said good course, and let's say 0.3 said it is 0.2, let's say 0.2 said that it is so-so, and 0.1 it is bad course. Now we have probabilities based on the survey that we have done. Then we take like a group of people, like 7 students, okay, and what is the probability that out of these 7 students, 2 say that it is excellent, and 1 said it is very good, and 1 said it is good, and let's say 2, 3, 4, and 3 said it is so-so, and 0 said it is bad. So now we are looking for probability that x1 equal to 2, and x2 equal to 1, x3 equal to 1, and x4 equal to 3, and x5 equal to 0. Okay. This probability could be computed in this way. So here n is the total number. It is 7 factorial, divided by x1 is 2 factorial, times 1 factorial, times 1 factorial, and so on. And times the probability for each event. So the probability that they say it is excellent is 0.1, so it becomes 0.1 square, and the probability 2 is 0.1 also, 0.1 of the power x2, and so on. But remember that the number of xi, the number should be the same as the number of the sample that we are checking. It is 7. So 2 plus 1 plus 1 plus 3 plus 0 should be 7. And also the total probabilities should be 1. So 0.1 plus 0.1 plus 0.5 plus 0.2 plus 0.1 must be 1. So this is called the multinomial distribution. It is widely used, and also it is important later when we see how to derive some algorithms based on this multinomial distribution. This is one example about it. Another kind of distribution is called Poisson distribution. What is Poisson distribution? What it means? Okay, now if we have in time, for example, if we have some event, it can occur randomly any instant of time. So it can occur randomly. For example, we don't have any information when it occurs, but we have some measurement that the rate of occurrence. For example, what is the probability that this data show lamp will damage, let's say, 4 times within 1 year, for example. So based on history, we have the rate of damages for this lamp. Let's say the rate is 2 per year, 2 times per year. Okay. Now we are looking what is the probability that it will damage 4 times within a year, or 10 times within a year. Okay, and it can happen any time, quite randomly. So we don't know when it happens exactly. Okay, so this case we can formulate it as Poisson distribution. So the probability that you will have I times x equal to I is equal to e to the power minus lambda t. T is the number, is the period of time. Lambda is the rate per unit time. Okay, for example, t in this example, let's say what is the probability that it will damage 10 times within 5 years. In that case, t equal to 5. Lambda is 2 per year, so it is 2, and we can compute it in this way. So this is called Poisson distribution, and we can prove that Poisson distribution is a limit for binomial distribution, but we can skip this one. Okay, and in case of continuous random variable, in order to calculate the probability of certain random variable to be within a and b interval, is the integration from a to b f of x dx, and also we can calculate the CDF as in this way. Now we are going fast also to present few random variable or probability density function, famous probability density function forms. The first one here, and actually the simplest one, is the uniform. This is called the uniform distribution from A to B. We know that the area must be 1. The area of the probability density function must be 1. It means that in this case, the height of this square should be 1 divided by b minus a. A and b can be, of course, positive or negative, so it gives you some indication how the random variable is distributed. So this is, for example, from -1 to 5. It means that the height will be 1 divided by 6, because here it will be 6, and the area should be 1. Okay, what it means here? this is the f of x means that the distribution of x is a random variable. Here x can take any value from -1 to 5. What is the probability that you be less than -1 is equal to 0. What is the probability that you are higher than 5 is 0. There is no chance unless to be between -1 and 5, and it is like equally likely. It is similar to the equally likely event, because if you take any interval, for example, here from, let's say, from 3 to 4, okay, or from 3 to 3.2, for example, is the same as from 4 to 4.2, as far as it is the same width. So it doesn't matter where you take the probability, so it is always the same probability. So this is the reason that it is called uniform distribution. The other distribution is called exponential random variable. It is given by this way. So it is the exponential distribution. Okay. We have also gamma distribution. Okay. And we come here to the most important distribution, and I'm sure that you know it. It is the normal distribution, or in telecommunication we call it Gaussian distribution. It is the same. So it is normal distribution. Normal distribution is given by this formula. So it is n normal. We have mean mu, and we have variance sigma square, and it is given by this equation. And this is the shape of the Gaussian distribution, where it is depends on the mean. So you can see that in the middle is mean, is 1. So Gaussian distribution is symmetric distribution. So the mean is the same as the median and is the same as the mode. Okay, so this is all of them, they are the same. And as you increase the variance, as you can see that you get flatter distribution, as you can see it with different variance. Variance is the scattering of your data around the mean. The scattering of your data around the mean. So it describes also some like the randomness in data. So as you have, if you have sigma square, if your variance equal to 0, it means that you have deterministic, because the same will be the mean. For example, if you have data like the mean is 1, so if your data is 1, 1, 1, 1, always 1, what it means? It means that the mean equal to 1, but also the variance square equal to 0, because you have the same, always you have 1. But if you have 1 and let's say 0.5, and you have, let's say, 0.9, you have 1.2, 1.1, and so on. So you can take that the mean is 1 and the variance is something, let's say, equal to, let's say, 0.1 or 0.2 or whatever. Okay, but if you have, let's say, 500, 1 minus 300 and minus, let's say, 100 and plus, let's say 250, and in order that when you take the average, it gives also 1. Okay, but here the variance will be much larger than this variance, because the data is highly scattered around the mean. Is not close to the mean. As the variance is close to 0, it means that your scattering of data is very close to the mean. If it is high, then your data is highly scattered around the mean. Okay. Why the normal distribution is the most important distribution that we will see in this game theory course, in machine learning course, or in general in data analysis. Generally, that the normal distribution is the most important distribution. We have several good reasons for that. The first reason, that it is called central limit theorem, that if you have random variable, let's say x1, and this x1 belongs to some distribution, any distribution, okay? Any distribution. You have x2 is independent of x1, and it belongs also to any distribution. Okay, and so on. So you have many like independent random variables. So if you take the summation of xi from I equal to 1, from 1 to n, if you take summation of many random variables, they are independent to each other. Always they converge to be like normal distribution. They converge to normal distribution regardless of the distributions of the events of the random variables themselves. They are converged to be normal distribution. So this is one feature of the normal distribution, and this is actually very much useful feature, because in many situations we are observing some behavior, but this behavior is a result of many like other or it is affected by many other factors that we don't know them. So the result will converge to be Gaussian distribution. Also, it is called or normal distribution. So, and also the distribution itself, it can represent also, or it can approximate many different other distributions. For example, binomial distribution can be approximated as Gaussian. Boson distribution can be approximated as Gaussian. T distribution can be approximated as Gaussian. Many different distributions can be approximated as Gaussian under certain conditions. So normal distribution is very important. Also, it has the highest entropy. In information theory, the highest entropy is a normal distribution. Actually, normal distribution is extremely important distribution, and many machine learning algorithms, especially in classification and regression, are based on the assumption that the original data is distributed with normal distribution. Because of that, I will concentrate more in this part on Gaussian distribution. So the CDF of the Gaussian, as we know, that it is the integration from minus infinity until a or till a. But the problem that this function doesn't have closed form solution. This integration, we don't have closed form solution for this integration. What we mean by closed form solution, we mean here that this integration cannot be represented as set of elementary functions. What are the elementary functions? Binomial, trigonometric for sine, cosine, for example, exponential, and so on. Logarithmic function. So we have set of elementary functions, but the result of this integration cannot be represented as in elementary function form. In that case, we have expressed it in a new function that we name it like error function. We call it error function. You can find in some calculators and also in every package that you can calculate this error function. The error function x is given by this formula, or we can also represent by what is known as a Q function. Okay, so the Q function gives us the probability in the tail. So this is the CDF of the Gaussian distribution of the normal distribution. This is the CDF. It starts from close to 0 and goes to 1, and it is very smooth. And at 0.5 of the CDF, we have the mean and the median and the mode. So the Q function also to calculate the probabilities, but we are going to skip this as well. Here I show using MATLAB how to calculate or how to emulate the Gaussian distribution and how to find the probabilities out of that. Okay. Multivariate normal distribution is also very important, because here we have multiple like random variable, and this is the situation when we have in machine learning. Usually we have multiple attributes from x1, x2 until xn, for example. So, and then we have some output y or classes or regression or whatever. So in that case we have from x1, x2 until xn. So if this distribution has normal distribution, we call it multivariate normal distribution. So we put it as x bold, which means that we have x vector here from x1 until xn. And in that case, the distribution is given by this formula. So it is 2 pi of the power of n in the number of independent or of variables x, n divided by 2, times here means the determinant of the covariance matrix R, and we take the determinant of this. Okay. So and then we take the half here, the square root of the determinant of the matrix, and e of the power minus half x minus mu x. Here it means that e minus half. Then we have, for example, x1, x2 until xn, I will do it like one by one. Minus mu1, mu2 is the mean. Mu1 is the mean of x1. Mu2 is the mean of x2 until mun, and then we take the transpose. Okay, times R, x is the covariance matrix. We will explain what is the covariance matrix in the next slide. Then multiplied by the same, but without transpose. So it will be x1, x2 until xn minus mu1, mu2 until mun. Okay. So this will be this one will be a single element number. So because if we take only two elements, for example, if we say that it is x1 and x2, then the first one will be x1 minus x2. Of course, here we have transpose it as well. Yeah. So x1 minus mu1, x2 minus mu2 times rxx will be 2 by 2. This will be 2 by 2. This is 1 by 2 because 1 row and 2 columns, and this will be also again x1 minus mu1 and x2 minus mu2. So this will be 2 by 1. So if you multiply 1 by 2 by 2 by 2, this will give 1 by 2. 1 by 2 vector times 2 by 1 gives 1 by 1. So it gives us a scalar, not vector. So this we can take the exponent of a scalar, of course. Okay, and here we represent the x as normal distribution with dimension n. We put the dimension here n, and we have vector of the mean values, and here we have the covariance matrix Rxx. The covariance matrix is the expected value. We're also going to explain what is expectation. X minus mu x times x minus mu x transpose, and it is given by this matrix. So we in the diagonal we have the variance of every element, but here we have the covariance between x1 and x2, the covariance between x1 and until xn. Okay. The correlation between two elements xi and xj is given by the covariance of xi and xj divided by the standard deviation of xi times the standard deviation of xj. And this we can also compute the distance between between the mean and certain x by using this. This is Mahalanobis distance in the n-dimensional space. Okay. In case that we have independent x, then it becomes much easier to represent the covariance matrix because the covariance between any xi and xj, if I does not equal to j, equal to 0 in case of independent elements. Because in that case you can take everyone alone, so it becomes like expectation of xi minus mu xi is 0 times expectation of xj minus mu xj is also equal to 0. So we have zeros everywhere except on the diagonal that we will have the variance of every element. And this is the case of projection. If you have vector x, which is normal distribution, and it is projected with some weight w transpose, then we have scalar element here z. Okay, and this z will be also Gaussian, and this is or normal, and this is one feature of normal distribution, that making any linear combination of normal distribution generates normal distribution. The distribution will not be changing as far as the process is linear, and this is one feature of normal distribution, that it will not change. What is going to change? Only the mean and variance can be changed, but the distribution itself will not be changed. So if you multiply, for example, you have z, let's say, equal to w1 as weight, w2, and I have here two distributions, two random variables. They are governed by multivariate normal distribution, x1 and x2. So this is x1, it is given like f of x is given like 1 divided by 2 by n is 2 divided by 1 is 2n, and then we'll have r x half e and so on. So now z equal to what? Z equal to w1 times x1 plus w2 times x2. W is just weight. just like waiting for x1 and x2. Here, the distribution of z will be also Gaussian or normal. So this will not change the distribution. What is going to change is only the mean. So the mean of z, expectation of z, equal to w1 times the expectation of x1, which is mu1, the mean mu1, plus w2 times mu2. So this will be the mean and also the variance. But this I'm going to explain maybe next lecture in more details. So z will be also normal distribution. This is the mean, and this will be the variance of this z. And also in case that if we have vector z, for example, assume that we have z1 and z2 equal to, let's say, w11, w12, w21, w22 times, let's say, x1 and x2. Okay, so in this case we have z1 is z1 and z2 will be also multivariate Gaussian or normal distribution. Okay, a chi-square, I'm going to skip this one. This is another distribution. Okay, classification of Bayesian. Actually, this is what we have already explained, but we are going to go further with this in next lecture, especially when we talk about risk. So how to classify data if you have a risk. So classification with Bayesian is not always that we select the class which gives the highest probability, because we need to take risk management into account. So this will be the topic of the next lecture. So the computation of the classification of data in case that we consider the risks as well. Okay. So is that, as I said, that I need to speed up a little bit because we have a lot of material coming and we need to complete this part as fast as possible. This is the reason that I'm trying to speed up the speed, but of course you can stop me if you want to ask any question. Thank you.